As you know, the Porcelli Lecture Series was started in 1973 in honor of Pasquale Porcelli, who was Boyd Professor of Mathematics here until his death in '72. His family set up a foundation account to have a lecture series inviting outstanding mathematicians and physicists to our campus each year. And so this is the 24th annual Porcelli Lecture Series. Although there have been a few years when we didn't have one, and if we did, it would be the 24th annual. It's been 24 years since it was founded. And it's a great privilege for me today to introduce Avner Friedman from the University of Minnesota, who will be giving one lecture today and two lectures tomorrow afternoon. I believe the first one is at 1:30 tomorrow, and then the next one is at 3. And I remind you, if you come a few minutes early, I was just told that there is a class in here tomorrow until 3 o'clock, so please, we'll try to get it organized, but please don't come in until 3. The man that had the class in here was a bit upset with people coming in. I don't know why, but it was. But here comes, it makes it just perfect. It's nice when a plan comes together. Here comes the overhead, so I will turn it over to Professor Friedman. Yeah, what, you want the overhead up here?
Yeah. Now the here, let's see what.
Thank you very much.
It's up there, I think.
I think what I said was wrong. We'll look at the chat. About the class schedule tomorrow.
Oops, it's too small. So maybe we should. Yeah, we get it down there. Oh. Oops. Let's see, is this video okay? Now, since this is the first of 3 talks, maybe I should give you an overview to what I have in mind. You know, I thought I will present to you several problems that the common thing to all of them is that they all came from industry. They are real life problems. Industry is very much interested in each of these problems, and they are not made up for as an exercise, but they really like to know that at the same to know the solution. And there is not just one solution and then you're finished, because every time you provide some answer, then industry will come with new questions. They would like to improve the model. And in fact, they're not even looking for a 100% solution, but just maybe for 80% solution. If they wait for the full answer, their competitor will come up with a better product. And without this source of problems from industry, no one perhaps would have thought about these problems. At the same time, they are really provide a great opportunity for people who do mathematics to challenging problems. In fact, the concept industrial mathematics, which is not quite a clear-cut concept, means that you do mathematics, but you start with the problems that come from industry. And your job is to solve these problems or to provide partial solutions, at the same time, in the process, inevitably, you will have to do also new mathematics as well as old mathematics. It was only a year or two ago that I ran into an article, about 40 or 50-page article by Bill Fry, who was the director of AT&T Bell Labs about 50 years ago. The article was reprinted, it appeared in the Monthly in 1940 or 1945, and it's called Industrial Mathematics. And he gives various examples how industrial mathematician approaches problems. He also says that the United States needs 10 industrial mathematicians a year. This was a perspective in 1945, before the computers became a standard tool. And he also gives example what the difference between a mathematician and an engineer. If you ask for the solution of x squared equal to 1, the engineer will say it is plus and minus 1, but the mathematician says no. First I will look at x to the n equal to 1, so I don't have to do the problem again when I will be asked to do x cubed equal to 1, x squared equal to 1, and so on. So this is the article. But anyway, the concept of industrial mathematics is not new. What is emerging now is because of job situation and so on. If you would like to have graduate programs, you have to enlarge the scope of the education, broaden the scope of what you prepare students to. At the same time, it's really appropriate for us, the faculty, to educate students to job opportunities of the future, and not to just the opportunities as they were until recent times. So, and this includes positions also, jobs also outside academia. So that's just a sort of general preaching about industrial mathematics. And what I want to do today is talk about, I picked up problems that you see them almost every day, at least once a week. When you play a phonograph or when you use a VCR, there is always a magnetic tape, and there is a head that reads the information from the tape. The magnetic tape itself involves lots of interesting problems about micromagnetics, but how you coat the thing on the magnetic material, this fluid which contains magnetic material, how you coat it on the substrate to create the film and so on. What I would like to talk about is about the head of the head that reads the information. So this problem came from 3M, but actually I ran into the same problem it came about 2 years ago, about 5-6 years ago in a company in Japan. They were also trying to model it. So, and any company that makes magnetic heads has this problem, which I'm going to tell you about. So, let's see, where is this? Okay. Okay, so this is a head, you can see here, and the tape is over here. There is a guide here and a guide there, and some kind of a motor that pulls the tape. So the tape rolls over the head, or if the head is above, it rolls underneath it, and with some velocity, v. What I wrote down here is the height of the tape, the profile of the tape. It's not a flat thing, so it's a function which depends on this, the coordinate x. And that's it. There is a problem here, and I'll tell you in a few minutes about it. Here is another perspective. I drew here the one-dimensional case. So there is a tape going through this guide, here and here. The space between the head and between the surface of the head and the tape, I call it h. H is a function of x, which goes along the horizontal axis, and time t. I put your time t because if the problem is time dependent. Later on I will take it to be time independent. The tape itself, its distance from the horizontal axis is u. So u is the inflection of the tape over the horizontal surface. And when the tape is above the head, the inflection is such that it lies above it with some positive distance h. Here's another picture. Same thing, but in 2 dimensions. So I hope you can focus on me when I'm okay. So here is h is a function of x and y. X is in this direction and y is perpendicular to the blackboard. There is a tape. T is the tension in the tape. These are the guides here and over there. And okay, that's it. Okay, now what is a good head that the factory can sell you? They would like it to be such that when you play your VCR or whatever magnetic tape, the tape on one hand would lie above the head, not touch it, because if it touches it, it will rub against it, you will not hear too well, it will wear out the tape. So it should be above it, but not too far from it. Because if the distance, h, the spacing, they get large, then the information from the tape to the head will be partially dissipated in the air. So you will not get a good signal from the tape. So the purpose of the designer is to create a head such that when you roll the tape would lie as close as possible, but not touch it. Hopefully uniformly. So you'll get the same sound. You will not have to, you'll not hear it going up and down. But there is a problem here. And the problem is that air is being entrained in the space between the tape and the head. And as things move with velocity v, the air is pressured into into a tunnel, and it creates here pressure. And then, just before the end, before the tape gets outside of the, from the end of the head, something funny happens. The spacing does this funny thing here. So here's a spacing, say, going from, let's see, 1, 0, 8. Okay, this is where the head is. The distance is more or less the same. And just before you get off the end of the head, the tape all of a sudden goes up, goes down, and goes up. That's the same. And the reason is this. Because while here, the air pressure is high because entrainment of air. But once it goes into the atmosphere, the pressure becomes 1 atmospheric pressure. Here it's higher. And this difference in pressure creates this bump. And that's very bad. Why? Because you would like the spacing usually between the tape and the head is about a micron. It's very, very small. It's about 1 micron. This thing by itself, it's about a micron. This stuff here, as you can see here, is about almost half a micron. That forces you to make the spacing here large enough so this will not rub into the tape. So you are losing here distance. You have to make the space higher. That means that you are losing also some of the signal coming from the tape, some of the information. You're getting it sort of pale or dissipated. So the question is, can we change the structure of the head? See, before I do a very nice profile of the head, a very nice, smooth, convex boundary. Can we do something else in order to get rid of this phenomena? Here is also a picture of the pressure itself. This was a spacing. Here is the pressure in the tape. You see the pressure is more or less constant. This is atmospheric pressure. This is the pressure while you are inside the tape, above the head, because of the air entrainment. See, the air is flowing into it. Take air from all over and make it pass through a narrow slot, and it's going to create pressure. And then, before it goes back outside, it does this bump. This looks like what people call maybe a boundary layer effect. So what 3M is interested, it was a company 3M, is how to design a head that will not have this phenomena. How do you reduce the impact of this boundary layer? How do you explain it to begin with? And so this is a two-dimensional problem, and computationally it's very difficult. And what they would like to do, in fact what they are doing, I think what every company is doing, is they are digging trenches into the tape, into the head. They are making some holes, deep holes, so air that goes above it has a chance to go inside and disappear. So if you buy a magnetic head, you will notice, I hope, that there are trenches there, maybe 20 or 30 small trenches to receive some of the air pressure and make it go away, in order to reduce the effect of the boundary layer, this swinging at the end. Okay, now the question is this. You have to dig, say, 20 trenches. Presumably, they will be circular or something like this. Where are you going to put them? Are you going to put them here, or maybe above, or on the side, or maybe all of them towards the end? What's the best way to dig the trenches? You can do experiments. You can just dig some trenches and then make an experiment, and if it then take another set of trenches, make another experiment. This is going to take lots of time and lots of money. In fact, time is even more important because every few years you want to come up with a new product. So the question was, can this be done, can this be modeled, can this problem be modeled, and can then we do computations that will be much faster than experiments? And that's where mathematics comes in. Can we understand what is happening using mathematical modeling? And furthermore, can we go beyond understanding and actually compute? So do the experiment on the computer and find out which is the best way, or which is a good way to eliminate this boundary layer effect, that this tremendous upheaval here near the end of the pressure. So that was a problem that was posed, and let me tell you how this is being addressed. First of all, what are the mathematical equations that come into modeling? So there are basically two quantities that I already drew before. One is the pressure, the air pressure, and the other is the elevation of the tape over the head. The pressure, see, air is basically, well, air is fluid. Fluid satisfies the equations of fluid, which are Navier-Stokes equations. These are complicated equations. Nonlinear, 4 equations, 3 for the velocity, 1 for the pressure. But if the fluid goes in a very thin, very narrow air space, then you can simplify the equations. You can get rid of almost everything except the pressure. This approximation is named after Reynolds. So it's a Reynolds equation. There is a pressure P. And when the channel in which the fluid passes has thickness as height h, the equation is, here is the pressure, there is a space in h, there is h, there is p, the pressure, there is h, there is p. The other quantities are just constants, epsilon, alpha, beta, and constants. So this is a differential equation. In one dimension, it's an ordinary differential equation. It's very, very simple because you see there is an x derivative of this, x derivative of this. So if you forget about the x derivative here and here, you just get this is equal to constant. So it's a first order expression equal to a constant for the pressure P. So you should be able to solve the pressure P in terms of h. But now what is h? Well, h was connected to the height of the tape, and the little spacing was h, and the difference was the height of the magnetic head, delta. So h plus delta is u, the deflection of the tape. So u is h plus delta. We know what delta is. That's the profile of the head that we are going to build. But we don't know what u is. We have to find it. And over the head, u is related to h in this way. Outside the head, there is no h, just u. Okay, so what's the equation for u? Magnetic tape is basically, can be modeled as a plate equation. You know, there are the equations of elasticity. We come to material, equation of elasticity. And then, more simply, but there is the equation of membrane. A membrane is something like a balloon, which basically is very thin. Its thickness is like 0. If you have some thickness to it, it behaves differently. It behaves like a plate. And a plate, the plate equation is a simplification of something more complicated, which is called the elasticity, linear elasticity equations. So the plate satisfies the 4th order equations, and for one-dimensional problem, it's a 4th derivative of u with respect to x times a constant, equal to basically the pressure, basically to the pressure that is on the plate. But the tape is also cooling. If you remember, there was a tension there. And that makes it sort of a membrane kind of behavior. And that's the reason for the second derivative. The equation for the membrane is the second derivative is constant. the plate is a fourth derivative constant. And here is a combination, so you have a fourth derivative of u minus the second derivative and equal to the pressure, or rather the excess pressure, because the tape is just in the, you put it in the atmosphere, it wouldn't do anything, it wouldn't stretch or anything. If there is an excess pressure, then it starts to stretch or to warp and things like that. So this is, 1 is taken to be the atmospheric pressure, and this is P minus 1, the difference of the atmospheric pressure. There are various physical constants, but I just lumped them all and into a few, or let's say, what some people say, we non-dimensionalize the problem. I mean, the change of variable, getting rid of all the, sometimes the product of two physical constant comes, we just take it as 1. Or we take certain units. When we non-dimensionalize, we introduce numbers that don't depend on units. And that helps us because we will know what in the equation is the big coefficient and what is the small coefficient. Remember, we don't need a 100% solution. So if you can approximate it, it will be good. So this is the equation for the deflection of the plate with height u. This is the equation for the pressure, and they are coupled because to find P, you can find P if you know H, but to find H above the tape is from L1, I'm sorry, the head is from L1 to L2. To find H for H between L1 and L2, you have to know, or you have to know U, but you are, so 0 to L, the tape is all the way from here to here. The equation of the deflection of the tape U, this is U, is all the way from 0 to L, and between L1 and L2, U is equal to the profile of the head plus the spacing. The conditions on U are at the guides here. U is fixed at 0 and it's horizontal. The derivative is 0. The same thing at this point. U is 0 and the derivative is 0. So these are the two equations. You are supposed to solve them, and then you will find out, write down the solution, you look at the profile of H, and you will see what you get. And then you'll get this bounded dimension. If you take a delta like this, you'll get this bound. If you take a delta with trenches, maybe you'll not get the bound. But the problem that they were interested in 3M is how do you compute as fast as possible the solution to this system. Once they know it, they're going to try with various different heads. They wanted a method to compute it. They wanted an algorithm. Now, in one dimension, this problem has been tackled by a number of people who did various computations. You can find them in textbooks even. And but even then, it's not always a very nice problem. And the reason is, although this is an ordinary differential equation, and this is an ordinary differential equation in one dimension, two ordinary differential equations, this is essentially the first order. Yeah, and you see, by the way, so P is coupled to H is connected to U, and U satisfies the equation with P here. So that's a couple. It's not clear that this even has a solution. In fact, I don't know if this system has a solution. No one knows if it has a solution. It's not been solved in general. Maybe for some range of parameters, but not for all of them. And it's not clear that there is one solution. So this is a problem that, they have, in fact, they have problem with the numerical methods. One of our industrial postdocs worked on this problem numerically and got some reasonable results. And then they asked them to do it in 2 dimensions, where really they are interested. You see, in 2 dimensions, you have a tape. Not only it oscillates before it leaves the head, but also the sides of the tape oscillate. And that causes them lots of grievance, because you don't hear very well because of this. And just all along the head, the sides of the tape oscillate. Well, that's nature, we can't do anything about it. But what we can do, maybe design a better head. So what they are interested is numerical methods, good numerical methods for 2 dimensions. Now, as an analyst, I wanted first to see if I can prove that there is a solution to this problem. And there is another difficulty, that H has to be non-negative. So it's not just solving 2 equations, but solving 2 equations with a constraint. In fact, H should be strictly positive. That's what we are after. I mean, we know that there are such solutions because we see. I mean, we all use magnetic heads and so on. We know that tape lies above it, so we know that there are solutions, but maybe the model is not correct, or maybe the range of parameters is not the one for which. So that's the problem. A year and a half ago, I worked on this with a former student of mine, and we tried to show that these 2 equations, at least in 1 dimension, has at least 1 solution. And we really could do that very easily. So in frustration, we said, look, why don't we take a very, very simple case, see if we can do it there. Let's take epsilon to be 0. So all this is gone. Let's take eta to be 0. So this is gone. Okay? So now you have the pH is constant. So take this P, which is P is a constant over H, and plug it here. And then you get a simple equation, 2nd order for U. I have a circuit here which I don't want to show you. So here is what we get. P times H is constant. So we put P equals 1 over H. And at this point L1, the pressure is 1. The pressure is 1 because here's atmospheric pressure. Here is atmospheric pressure. So here the pressure is 1. So if P is 1, and H will be the elevation at the point L1. So this is which is, so H is U minus delta. Actually, it's too many pens here. UL1 minus delta. So the equation becomes the second derivative of U is equal to minus a constant times P minus 1 times above the head it is 1 and outside the head it is 0. Because the pressure is 1, this becomes 0. So I can put here the characteristic function of L1 and and I put for P this what I found here, so this is the equation we get. The second derivative of U is a constant times the value of U at this point L1 minus the height delta, and this is U of x minus delta x. Because then after we found the constant, we have to put, after we found the value of the constant, we have to put it here. So So P is this constant over H. This is the constant, and this is H here. This is H, U minus delta. This is the constant, minus 1. And in this interval. And outside this interval, U is linear. U, because second derivative is 0. And U is 0 here and here. Okay. Okay, something happened. I first had an equation of the fourth order for U, but I made this eta 0, so I got second order. For second order, I cannot have 4 boundary conditions for ordinary differential. I had to throw 2 of them, and I just had to do it in a judicious way. And it seems like I should throw away the higher order derivatives. That's why I got U equal to 0 and UL equal to 0, and I threw away the derivatives at 0 and derivatives. Now, why did I throw these derivatives? I'll tell you a little bit why. But anyway, look at this problem. This is not an ordinary. So it's not an ordinary ODE. Because the unknown function U also appears here at this particular point, U of L1. So it's not clear that you can actually solve it. So what we do is something called shooting method. We take U at 0, then we guess U prime of 0 equal to, say, lambda, and we start changing lambda continuously until we reach a particular, hopefully, a particular value such that at this endpoint the solution will be equal to 0. So we are shooting in a direction which we keep increasing until it finally falls where it should fall. That's a shooting method that we use, but we have no other way of doing anything with this. And it turns out that this problem does have a solution. As we raise the lambda, eventually we do hit here. But we don't know if it's the only way. You can, if you take a hose, and you want to reach with the hose from one point to another, and you can do it with an angle less than 45 degrees. You can also do it with an angle bigger than 45 degrees, just that, it's close to 90 degrees. There are 2 solutions. There may be here also other solutions. Under some assumption, there is actually only one. But anyway, let's stick with this one. So now, what is the situation? So we have done here a great thing. We solved a very special problem. Epsilon equal to 0, eta equal to 0. So we are very happy because it was not so simple to show that this is a solution, but it's only a very, very special case. Then I remember that as an applied mathematician, you are supposed to look at the size of the constants. And that's what we just opened the dictionary for all the various quantities and computed, and we found that alpha is like 1, beta is the size of 1, epsilon is like 1 over 100, or 1 over 200, and eta is like 1 over maybe 500. So these are very small constants. So taking them to be 0 is not such a bad idea. Well, can we solve this problem with small constants? You can do it for 0 constant, but can we show that we really cannot, if you take epsilon and eta small, that actually there is a solution which comes close to what we found? And the answer is yes, and that takes a lot of analysis to do. Because this is a singular perturbation problem. A singular perturbation is a problem such that, say with the parameter epsilon, such that when epsilon is 0, something drastic happens. The order of the equation drops down. And if the order drops down, some boundary conditions have to give up. Let me give you an example. Here's a simple equation. Epsilon u double prime plus u prime equal to 0 between 0 and 1. And u of 0 is 1. And u of 1 is 0. So setting derivatives, so you want to find a solution that connects it. Of course, we know what the solution is. It's a linear combination of the two homogeneous solutions. One is a constant, right? And the other is u e to the minus 1 over e to the minus x over epsilon. So yesterday I solved the problem, and I found out that these are the constant, e to the minus 1 over epsilon and 1. You can verify it. If x is 0, this disappears. Wait a second. And yeah, x is 0, so e to the minus 0 is 1, so you get 1. And if x is 1, you get minus e to the minus 1 plus e to the minus 1. What happens when epsilon goes to 0? You are going to get first order equation. It cannot satisfy two boundary conditions. One of them has to disappear. Which one? Or maybe both, maybe something else. Well, we can test this particular case. If x is between 0 and 1, if x is between 0 and 1, this, of course, e to the minus 1 over epsilon will make it go to 0. And e to the minus x over epsilon, if x is bigger than 0, this also disappears, goes to 0. So the whole thing goes to 0. So what we get is a solution which looks like this. Goes from 1, very fast, go near 0, exponentially in fact. But it always, for any value, when x of epsilon, when x is 0, it is 1. So it's like that. This is a boundary layer phenomenon. You know, the boundary refuses to give up its boundary value. It has to satisfy it for any epsilon. But the equation demands a change, because the limit has a change. They are fighting each other, and the fight, like in every fight between two countries, it starts on the boundary, on the border. So there you are. So there is a clash here, and you get the boundary layer. The same phenomenon occurs in more complicated equations. So the fact that we were able to, you know, as I said, we were able to solve this very special case when both are 0. And remember, we have to explain the boundary layer thing with the h. The explanation is that after you check all the constants, you find epsilon is small, eta is small. So this is really a singular perturbation problem. This coefficient is small, and this is small, and we are going to use boundary conditions. For instance, for P, we are going to use boundary conditions for U, and what I gave you as a special case is, in fact, what we lose is what I gave you before. We're losing the U prime equal to 0 on both sides, and we are losing for the boundary condition for P on this side. These are mathematical statements. And so that explains the phenomena that we have to think. And it's funny because the engineers have been computing and computing and computing, but they never noticed that there is really a boundary layer thing. In fact, we didn't notice it. It was just by chance, because we couldn't solve the general problem and look at the limit case. And then we saw that it's a... So that explains the boundary layer effect, and so we can say that this problem has a solution. It exhibits a behavior that we saw experimentally, and it is known numerically as well in one dimension.
But now that we have an understanding of what's going on, let's go into the 2 dimensions, where there are no numerical results at all, because it's very complicated. Okay, so in 2 dimensions, I'm just drawing here above the head, we have this, I just draw the projection on the xy plane. This is where it was a 1 dimension going this way. But now we have to consider the 2nd dimension. What happens is that on this boundary, you have 2 boundary conditions which are for a plate which is unsupported. It's free to move, free to oscillate. The Laplacian of u is 0 here, and the y derivative of the Laplacian is also 0. And these conditions exhibit some unstable behavior if you try to do any computations with this. Now, we can compute the boundary layer near the boundary. Give me any differential equation with singular perturbation type and ask me how does it should behave near the boundary. I can make a change of scales to make this little thing size 1, and I get a modified equation. I throw away all the small terms, and I get the main term in the boundary layer. It's easy to compute. Okay? I can also here, there are formulas which one can use to compute boundary layer effects here. They are different than the boundary layers effects here, but it can be computed. And if you do that, and you try to fit it in with the limit case over here inside, and the solution is made up basically of 2 things. The limit case when the constants are 0 and boundary behavior. Catching of the 2 will give you a good approximation. And we can do this quite fast. And, but here is a problem. When we developed this technique, 3M went out of the business of selling. They had a product and they didn't want to do a new one. And now they're completely out of it. They sold out the magnetic tape industry. So that's the reason we have not followed up with the numerical computations in this. So, but anyway, this techniques is very promising. Now, it's true that all the theorems that we have, we don't have any theorem, mathematical theorem for 2 dimensions. We have a mathematical theorem for 1 dimension, for a convex things. But the numerical method, you can implement on anything you want. I mean, generally, you can do numerical methods for anything in the world, including the, let's say, including the the backward heat equation, for instance. If you want to solve the backward heat equation, you set T plus Uxx equal to 0. Say here, this is initially T equal to 0. You give some initial conditions T equals f of x, and you want to solve it here. We know there is no solution in general. It's a bad problem. It's an ill-posed problem. Sometimes it has solution, sometimes it doesn't. If this function f is not the entire analytic function, there is no solution. But you can nonetheless compute it numerically. For instance, you can approximate f by Fourier series. And for each term, you have the standard solution. But if you try to approximate too much, it breaks down. Because there is it's ill-posed problem. So you can always compute, but if there is no mathematical theory that says that there is a solution, your approximation will blow out. is to try to make it more precise. If it's not very precise, then we haven't really found a good approximation. If it starts to get more and more precise, it frustrates you and starts to blow up. If you take initial values that are like an cosine nx, the solution would be of the backward heat equation an cosine nx e to the nt. And you can see, because if t is positive, this is e to the nt is not series like this is going to blow up. Right? If you have a finite number, it's okay. But if you start to take a larger and larger number, it's going to blow up. So you need a mathematical theorem if you want to make an approximation, make a good guess. You have to have a theorem behind it. So for the tape problem, I said we have mathematical theorems for some cases. Therefore, I think we can finally have the courage of computing it even in 2 dimensions. But we need a customer for that. So, thank you.
Questions?
The model you were doing, that was just for the head without the holes in the
Without, yeah, this is for the head without the holes, and then we can mathematically prove that this has a solution and it has a boundary layer behavior. If you put the trenches in, then we don't have a mathematical theorem, because the assumptions in the theorem is that the head is convex. But numerically, we can compute it the same way. Therefore, you know, it's a good guess that one should try to use this approximation, this method with boundary layer to compute in any case. It's quite often the case that the computations go beyond what one can prove rigorously.
And which was the nil-post problem here? You ended up with the nil-post problem?
Oh, no, I just mentioned that you can always, if you took the backward heat equation, then we know it does not have a solution for general data, but you can try to approximate by taking a finite Fourier series. You can write down explicitly what the solution is, the same as initial data, but you put e to the nt. As long as you have a finite approximation of the initial of f of x, the solution is a precise solution. But if you try to, but as n goes to infinity, this series is divergent.
Yes.
So the solution starts to oscillate. Therefore, you cannot, by approximation, construct a solution. So the danger in any problem which is time dependent, you can try to find a different scheme. But does it converge? Well, if there is a mathematical theory that says that this problem is well posed, you expect that it will converge. If you satisfy some kind of condition, stability, or whatever it's called, But if you know that the problem is ill-posed, no matter what you do, it will not converge. What I'm saying is we have some theorems that say we can solve the tape equations in a certain way, and there is a boundary layer effect and so on, if the head is convex. That if it's not quite convex but a little bit non-convex, also it will be true, just by stability. If you put a little bigger trenches, we have to try it, but it's worth, for a company which spends a large number of dollars on making heads, it's worth trying this method, which is completely different. It's completely non-standard. And we started to work on it about a year and a half after it was a big project for them for a while. Every year the project changed, or sometimes every few months the project changed. If we don't do it on time, then we're not have interest at that time. They'll come back to it eventually, if they still own this technology. But in this particular case of 3M, they sold the magnetic part of the company. And, but however, this is, now I want to do some work here because you do computations and things like that, it may not necessarily work out very well at first. There will be all kinds of tricks to do and so on. But this approach is one which can be done in maybe real time, so that the designer can make a design and within 10 minutes find out what's the outcome. I mean, I don't know if it's going to be 10 minutes, but right now they have to wait. Maybe a week every time. Use the clay and wait a week. You can't do that. It's too expensive. So that's an example of a problem that has some interest in mathematics and can be of great value. But the story on it is not finished because we still have, we'll come back to it when appropriate time. Yes.
Is there something about the way a head reads a magnetic tape that says you can only control it? Why couldn't you put grooves along the top and get some kind of airflow that way that might...
Say it again?
Why couldn't you, for example, make grooves across the top of the head as opposed to trenches? You had your vertical trenches.
Oh! You mean,
that would totally give you different equations or something.
You put something on the top, you mean?
Some kind of grooves so the air could just flow, wouldn't be, I don't know what that would do. I mean, that's my, when you get to a differential equation, you can talk about solving differential equations, but it seems to me that this physical problem has an infinite number of possible configurations you could imagine.
Yeah.
Why go with the trenches from the outset? Is that one constraint?
They can make, you mean to put on the top something else with grooves.
Yeah.
It's another possibility, yeah.
And then I also...
But I know that they do make trenches on the head.
And then I suppose you talked to them a lot before you spent too much time working on the mathematics. So what occurred to me, why couldn't you simply reduce the amount of air, make partial vacuums?
So you can reduce. The amount of air comes with the velocity. You are in the environment, 1 atmospheric pressure. You have a tape that is moving in a very narrow, creating a very narrow channel there with a certain velocity, and it creates air entrainment. Nothing you can do about it.
You can't just make a partial vacuum, it's too expensive or something like that?
Yeah, I think so.
Can you tell us a good way, a successful way to solve the problem of the design of trenches? What is one good way that works?
I don't know. There are two possible solutions. The first one is that you just look at the head and see what it's like. Maybe more. The trenches actually are not done by holes, but rather they go all along. The second way is that it may be a proprietor, I think. I don't know. But they showed me, they are doing trenches along the whole thing, not just the hole. I mean, grooves along the whole thing, yeah. And I think only on one side, but having opening on the other side, it's might, maybe you should patent it. Yes.
Is it the air pressure that keeps the tape from touching the head?
Yes, the air pressure keeps it from falling. So if you make too many trenches, it just falls.